Hi, and welcome to the presentation of our paper. Our research topic is virtual sports simulations, and we took a closer look at golf putting. Because golf putting is a good case study for skill-based sports, as it requires high precision, haptic feedback, and spatial perception. This work is in cooperation with the University of Hamburg and Padview, who are putting experts building AR training solutions. I'm Felix, and my colleagues are Kili and Frank Steinecke from the University of Hamburg, as well as Fabian Lehter and myself from Padview. So why did we investigate sports simulations? First of all, VR enables flexible ways of training, with the biggest benefits being that there are, for example, less space constraints and the loss for a controlled simulation. There's also a problem that VR can miss multimodal cues, such as haptics and proprioception, which is needed for fine motor accuracy. So here we identified a gap between the real-world execution that offers the best sensory fidelity and the VR simulation that enables flexible, controlled, and adaptable training. So we also looked at augmented reality. It enables adaptive training, but it misses flexibility of a virtual simulation. As we want to retain as much fidelity and favor the flexibility of a virtual environment versus the real golf course, like the real putting, we also looked at augmented virtuality. In augmented virtuality, we're blending real elements back into a virtual simulation, and we propose this could be a sweet spot for precision sports by balancing realism with flexibility and control. So in our paper, we built and evaluated a putting simulator that features virtual reality and augmented virtuality modes. Our central research question was, can augmented virtuality bridge the gap to real-world putting while retaining VR's flexibility, improving putting performance, realism, and experience? What we know from related work, for example, of the colleagues Hans Lubers and Johnson here on the left, is that a real golf putter in a virtual putting simulation was leading to more accuracy of putting as well as more preference reported by participants in their study using a putter over a controller. This was most likely due to better inertia properties and tactile feel. Moreover, Harris and colleagues on the right here validated a VR putting simulation and found it to be valid but not yet equivalent to real-world putting. Both studies demand for higher self-representation. So we're trying to address this gap with our AV, augmented virtuality simulator. So our AV simulator is based on previous work, and it keeps the haptic benefits of a real golf putter and ball. So it has high interaction fidelity, but we're now also adding a pass-through based view onto the equipment through this window that you can see here on the floor. So the user's own limbs as well as the equipment is visible there. So we aim for a high self-representation fidelity as well. In our pilot user study, we evaluated our augmented virtuality approach and within subjects design, which was that very counterbalanced. We compared the VR and the augmented virtuality environments on a fixed distance of 7 feet and 10 putts per condition. We had a total of 36 participants, from whom 17 had no prior putting experience and 19 had some putting experience or more. The participants were situated on a putting green from Padview. You can see this here on the right side. This is myself holding a putter. You can see that there is a controller attached to the putter. This is how we obtained the launch vector for the virtual simulation. And in all three conditions, we use this platform, as well as a real putter and golf ball. And only in the virtual conditions, the headset basically provided the virtual environment around it, other than this platform. Our measures were in a two-dimensional approach. First was performance, obtained through external tracking from overhead, as well as from within the simulation. We focused here on miss distance and hold percentage as the previous authors. We also analyzed the user experience through task load, presence, preference, and simulator sickness. Moving on to our hypotheses, the first one establishes the real world as a baseline, whereas the second one assumes that the putting performance would be better in augmented virtuality compared to the classical VR simulation. And for our third one, we assume that the task load demands in VR are higher because of higher incongruencies and therefore lower in our approach. In H4 and H5, we hypothesized that presence and preference would be higher in AV or VR. So here you can see the condition VR. It's a traditional simulation. On the lower left, you see the real world view. Just for comparison, we use a real putter, a real ball, and virtual counterparts in our virtual environment, and you can see a lower body avatar also kind of simulating the feet of the participant. As for the AV condition, you can see here again a real putter, a real golf ball, And now this cutout on the floor visualizing the real lower body, the hands and the equipment of the participant. So as for our results, we analyzed the putting data separate for each data set as well as in 2 stages. So we had per participant and condition averages here on the box plots, and we additionally fitted mixed models to gain more insights on the individual putts. You can see those on the overlaid black dots and white whiskers. We found no significant difference on the external tracking data set for mean absolute miss distance, so like radial error on the left. But we did find it for a whole percentage that it was significantly lower in virtual reality compared to real world and augmented virtual reality. This data set was bound by a limitation, like the platform was bounded. Therefore, we're not focusing too much on this data set. And our analysis mainly focuses on this one. This is from within the simulation. So same analysis performed here, only on the virtual conditions to compare them directly from within the simulation. And we can see here that the mean absolute miss distance is significantly smaller in AV, promoting that putting was significantly better within the virtual simulation between those 2 conditions, as well as the hold odds were significantly higher in AV. Task load profiles paint a similar picture. We want to highlight here that mental demand, physical demand, perceived performance, and frustration dimensions were all kind of impacted, with mental demand and perceived performance being significantly higher or respectively lower in the virtual reality condition compared to AV and the real world, giving us a hint that AV is maybe close situated to the real world pattern here in terms of task load. For simulator sickness, this paints a similar story, as that VR increased simulator sickness in pre-post deltas, whereas AV was close situated to the real world putting. Presence, we found no significant difference from the IPQ between our both virtual conditions, AV and VR. So presence was already quite high, and it most likely C-linked, or the IPQ was not sensitive enough here. For the result summary, our first hypothesis was not confirmed, partly also due to the limitation of our data set, including the real world putts. So we focused our analysis on the virtual putts, and we could confirm for the virtual putts that the AV putting was indeed better than the VR putting. Participants performed better here. For the task load demands, it was at least in some subscales higher in VR, so we can partially confirm also hypothesis 3. And for hypothesis 4, it could not be confirmed, as the presence responses were kind of similar and no significant difference could be found here. For hypothesis 5, the augmented virtual reality condition was clearly preferred over the VR condition by participants. Restoring key real cues like the putter, the ball, and the own limbs in AV can improve performance, task load, and sim sickness, almost approaching real world performance. You can see this from our results, without really negatively impacting presence, at least not detected by the IPQ presence questionnaire. So therefore, we conclude that AV from our initial pilot testing can function as a sweet spot for precision sports, as kind of evident here in putting, and it can balance the fidelity and flexibility trade-off. However, also our study had some limitations, as earlier mentioned, with the real-world data set, which would be, again, work for the future to improve on that. So the platform boundary impacted our real-world comparisons that would need to be redone. And the tracking fidelity was also sometimes impacted by occasional glitches, but it affected only a very limited number of trials. And additionally, the limited full body tracking in VR might also impose a problem, such as that we approximated the feet in VR underneath the participant and did not do separate feet tracking. So this would be also left to future work to improve on those demands, to get a more fair comparison here. Also in general, like the generalization to other distances, maybe also disciplines, and also to expert golfers and putters would be interesting and left to future work. So our suggestions is to go with varying distances and slopes when sticking to putting, to work on the geometry of the paths for cutout, to see how that influences the performance, as well as do more pass-through enhancements to, strengthen the self-representation in the simulation. Additionally, evaluating the training and skill transfer to the real world would be also interesting. So our contributions are this new approach of AV within mixed reality as a skill-based putting simulator, and our controlled evaluation showing that AV, at least in putting performance, as well as on some user experience measures, was outperforming VR. And we identified the benefits of AV generally for precision sports being kind of that sweet spot between fidelity and flexibility. And as mixed reality is a pragmatic path for precision sports, we conclude we want to see more applications of the like. Thank you very much.